of the education and programming group here, and myself and Bruce Mabrito, who some of you probably know, uh, go to great lengths to try and bring you some education and some interesting programs. And in doing so, the last couple of years, what we've taken as feedback has been from what some people might remember as an open mic night. And we did this back at the old campus of the building that we used to meet at. And um, there weren't that many people there that evening. I think there were only 21 individuals, but we had some really great ideas that people threw out. And those ideas we've pretty much gone through and tried to hit on a lot of that. And so that's why we wanted to have another survey that went out and canvassed you all for the types of programs that you want to see, the types of events that you want to see. So I did err on the side of more education and continuing education. I did not hit very hard some of the Six Sigma and Lean Six Sigma type of events. I kind of went in some of the directions that we've seen over the past couple of years with COVID and environmental factors that we've been going towards. Hopefully, those of you that did read through the survey found it just a little amusing. But to hit on question number one of my biggest concerns was kind of getting to the venue. And do people want to try and meet virtually? Do they want to meet in person? Or did you want a hybrid? So the question that I asked was the format in which I most enjoy receiving educational offerings from ASQ 1404 San Antonio is, and basically the answers were virtual live learning. I don't like to drive and would rather sit at my computer and heckle the speaker. And that was 52% of you. So we will try and do most of our events for the remainder of 2022 virtually, mainly because we don't have a venue right now to do a physical location. But we are trying to find some place that can handle the people that we're looking to gather around. That being that we have invited several of the universities to participate with us. So just so you know, 33% of the individuals that responded, and there were about 27 people that responded, and that they would like to hybrid, where they had some events that were virtual and some events that were in person. So we will try and hit both of those this year and into next year and have some events that cross over and potentially do both. The second survey question that we asked, or I asked, was the subjects that interest me regarding logistics include supply procurement, vendor selection, vendor qualification, vendor metrics. None of the above. I say please, and it appears. Please don't ask me how they do it. And so of those answers, 59% of you were interested in vendor metrics. And I know that Ned is probably going to talk a little bit about just basic metrics and statistics tonight. Obviously, he's going to be doing statistics, and we might get into statistics in general for some of our vendors. And at some point in the near future, we might get a little bit more into that and determining how qualified your suppliers are, looking at vendors in general and how to grade vendors. The next response that was highest on the list was obviously those vendor qualifications. So vendor metrics and vendor qualifications, we will try and hit on those this year. Question number 3, and again, there are only 4. Subjects that interest me regarding technical writing or labeling include And there were 1, 2, 3, 4, 5, 6 answers, and then a none of the above. And I had instructions, directions for use, writing procedures, writing V&V protocols, verification and validation, writing requirements, writing service documents, writing quick guides, or none of the above. I don't even ask for directions. Why would I read them? And with this, we had 52% of people were interested in writing V&V protocols. So we will definitely try and hit on V&V protocols, writing them, potentially performing those. And the second group, where we had the majority of responses, was in writing directions for use and instructions for use. And then the third, which was a close almost with the directions for use, was writing quick guides. So we will definitely try and get into some of that labeling and instructions for use, some of the V&V, basically kind of getting into more of that technical writing and how to get your point across a little bit more succinctly. And then I did have a category of miscellaneous subjects that interest me. And I said, interest me include, and I had quite a few subjects in here, how to develop a standards checklist. And I'm just going to read the percentages that I had answer. For that, I had 42% of you said you were interested in that, because I basically allowed you to answer as many times as you wanted. How to write a more effective CAPA risk. 46% of individuals wanted to know how to do that. Assessing audit readiness. 50% of the respondents said, I want to be able to know if I'm ready for a true audit, whether that be from the FDA, whether that be from OSHA, whether that be from whoever has to audit me. I want to know if I'm ready. And again, it's my first audit. What do I do? 15%. How do I get into project management? 31%. I'm not even going to read the next one because it was a low percentage. Meeting etiquette, how to effectively run a meeting from invite to beyond, and that was 20%. Next one was, I want that job, and 15% of individuals were interested in that topic. Change control, 38%. Design control, 34%. Lean Six Sigma, 38%. Climate change, 31%. Food and quality industry in San Antonio, 35%. And what does drought do to our area in the short and long term? 23%. So we did have some comments on that. And out of the comments, thank you for whoever put this forward. There was no name on it, but we did get potentially our speaker for next month. So I wanted to thank anyone who put that in, and Bruce may pop into this and tell us that he was able to procure this individual. But we did get Dr. Ron Green was brought to our attention to talk about what drought does to our area, both long and short-term effects. And so he may be speaking to our group in the next month about that very topic. So if Bruce is on the phone right now and has any of that, he may be able to chime in. I don't see him right now, but if he pops up in the next couple minutes, that's great. I wanted to open it up and allow people to kind of throw out any subjects that they might be interested in for the next couple minutes. And I am taking notes, and we are recording this. So if anybody has any subjects that they're interested in, if they want to put it in the chat, if they want to go ahead and unmute themselves, I'd be more than happy to list out some of those topics and try and get to them. Anybody? Okay. Well, you have the chat to go ahead and do that. Should you? Oh, oh, Kappa. Any specific topics on Kappa? Just Kappa in general? And quality strategies. And Brenda, thank you for joining us all the way from the Carolinas. Anybody else with any topics that they want to see? Okay. Well, I'm going to go ahead then, and I'm going to introduce our speaker, Ned Schneider, and he's going to be going over statistics overview and aha moments. And just to give you a little bit of background on Ned, he's been a consultant and trainer with Quality Improvement Consulting and Training Team, LLC. He has 20 plus years of experience in the medical device industry as a project engineer and engineering director, working for several leading technology companies. He's received corporate awards from 3M, Allergan, and Advanced Abbott Medical Optics for outstanding performance. He's had that because he's significantly improved product and process performance, reducing costs, and that included saving them millions of dollars annually. He really puts this into the category of his project success resulted from using design of experiments to gain new knowledge about product and process performance necessary for breakthrough business results. He's compiled patents over the course of his engineering career, and he has a BSME and B Industrial Engineering and Management. He teaches ASQ certification refresher classes for Six Sigma black belts and certified quality engineering programs. He's taught design of experiments for UC Irvine and UC San Diego through their extension and corporate training programs. He's an ASQ certified Six Sigma black belt and certified quality engineer, and he has a lot of expertise in the area of product development, process development, and automation. So if we could all welcome Ned tonight, that would be great. And if you could hold your questions till the end of his presentation, that would be wonderful. Ned is a recent relocation to Texas, and so we welcome him with open arms here. And I'm going to go ahead and mute myself, and I will read everyone's questions that they put in the chat at the end of Ned's presentation. Ned, I'm going to go ahead and give it over to you.
Okay, are you able to hear me? Ann?
Yeah, we can hear you.
All
Sorry
right.
about that, Ed.
Are you guys able to see my screen at this point?
Yes.
All right, great. Yesterday when we did a rehearsal, it was done for me. Any rate, we got there. So let's begin. And tonight's presentation, first of all, I want to say hi to everyone. Good evening, ASQ San Antonio. And I'm recently relocated from West Coast, I won't say where, to Texas, and I love it here. Okay, so tonight's presentation is a statistics overview and aha moments in statistics. Okay, statistics is a powerful set of scientific tools used to extract meaningful information from numbers. Top performing companies realize that business decisions based on data are much more reliable than decisions based on expert opinions. And this takes me back to my early days in 3M back in the 1980s. And my manager told me before an important brainstorming meeting that he said, Ned, going into the meeting, if you're going to want people to follow you and listen to you, you're going to need to bring data. And he said, in this company, we don't care how many initials you have after your name, BS, MS, PhD. He says, opinions are like belly buttons. Everybody's got one. And he says, we respond to data. So if you want to be persuading people to follow you as a leader, and I was a project engineer at the time, he says, bring data. Statistical tools provide the best means to take your processes from an art and make them a science, perform measurement system analysis and optimization, perform comparisons. We might want to know which material is best or supplier is best, which machine is producing the least amount of variation, which method is best, etc. Determine product and process capability, generate tolerance intervals for product or process inputs and outputs, perform product or process characterization and optimization, provide process monitoring and control, perform product and process validations, resolve CAPAs, and actually provide risk reduction due to increased product and process understanding. So if we've developed our processes and our products using statistics, we're going to have fewer instances of CAPAs. Common statistical methods and when to use them. First, I'm going to discuss applications for continuous data. And then anything you see written in red, any statistical tool in red, is distribution type dependent. In other words, the results, for them to be valid, we need to understand whether or not the data do follow a normal distribution. And the first set of tools I want to talk about briefly. Again, I put this together new recently, and I've got too much material, so I'm going to have to kind of skim through it. One sample, two sample t-test were devised to analyze small data sets. At the time, this was a big deal, a breakthrough, where statisticians could analyze data sets as small as 10 with statistical significance. And a one sample t-test could be used to compare your current process mean to your historical mean to see if there's been a shift. Two-sample t-test is used to compare two means. And you might want to be able to determine determine if you get more longevity from supplier A's or supplier B's component. And then when we want to compare three or more means to see if they're equal, we can use ANOVA, analysis of variance, and that utilizes the F distribution and the F test. And by the way, maybe you didn't know this, but the T distribution and the F distribution are related. The F distribution is the T distribution squared, so you get exactly the same result. Okay, a one-sample standard deviation test utilizes the chi-square distribution, and a two-sample standard deviation test utilizes the F distribution and again the F test. And you may be asking yourself, how is it we use the F test to tell us if means are different as well as if standard deviations are different? Well, that's a discussion for another night. I don't have time to go into that right now, but something to ponder. A one-sample standard deviation is used to compare a standard deviation to a target. And you may have done a repair, complex repair on your machine, and you may want to test the machine to see that the standard deviation hasn't changed due to the repair. You can do a two-sample standard deviation test used to compare two standard deviations. And then when we have three or more standard deviations, we can use Bartlett's test when the data are normally distributed, or Levine's test, or multiple comparisons test when the data are non-normal. And again, the chi-square test and the F test are in red, indicating that for these results to be valid, the data needs to come from a normal distribution. When the data doesn't come from a normal distribution, Minitab will provide an alternative solution using Bonnet's test. And that's a non-parametric test, and we'll do that a little bit later. Tolerance interval is an interval to cover a specified proportion of a population distribution with a given confidence level and is closely related to measures of process capability. If we have the population mean and standard deviation sigma, then the tolerance interval is simply mu plus minus z alpha divided by 2 for a two-sided tolerance interval times sigma. But when we use a sample, something where we don't have mu and sigma, but we're going to estimate it with a sample mean and a sample standard deviation, then the equation changes and z is replaced with a k. And this k value is based on sample size, confidence level, and the proportion within the interval. And the reason that we aren't using z anymore is because we have more uncertainty due to the fact that we are estimating mu and sigma from a sample. Tolerance intervals can be used to calculate process capability when you have a small amount of data. When you don't know, normally when you do process capability, you have the range for the spec limit in the numerator, and then underneath the denominator, we have 6 sigma. When you don't know what sigma is, a lot of people will use the tolerance interval range. when you have smaller samples, like maybe 10, 15, 20, may use that approach. And that's a valid approach. Again, too, when I've done some consulting and some of the class 3 device, medical device companies I work for, when we were doing process validations, the tolerance interval of our sample needed to be smaller than the range for our upper and lower spec limits. And it needed to be if we wanted to state that our process was capable. And if your process isn't capable, then you end up in a situation where you're probably doing 100% inspection. Modeling is performed to characterize product or process performance. Modeling can be done using ANOVA analysis, where most inputs are categorical factors, regression analysis, when most inputs are continuous factors, and DOE, when you can dictate specific combinations of the inputs to be run simultaneously. And DOE is the best of these options, and I think it's simpler, actually. And then generally, we use ANOVA or regression analysis when the empirical data already exists and we want to know what the data says. These experimental methods are used to identify significant inputs used to create a prediction equation. And then I've got a two-factor second order equation here, and that's what this would look like. And then that model can be used to generate a response surface, okay, of our output versus on each side, we can have two different inputs and we can see how the output changes. And because we have second order terms and an interaction term, you can see that we have a lot of curvature in our response surface. And then we can use these tools for sensitivity analysis using response surface methodology techniques. And so we can identify the optimum input settings while minimizing output variation. And then we can also use it to help us identify regions for tolerances for the inputs. And FYI, I've got an old set of data I was looking at the other day. And back in the late 1990s, they did a survey in Japan to ask them what was the most frequent tools that they used to improve processes and improve product performance. And at the top of the list was graphs and charts. Second, out of a list of about 25 tools, was DOE. And that might explain design of experiments. That's what DOE stands for. And that might explain why they are kind of the gold standard for quality. Continuous data measurement system. Okay, let's see. A measurement system analysis can be done to verify that your measurement system has appropriate accuracy, stability, precision, capability. Common methods used are bias stability studies, gauge linearity studies, GR&R, etc. A gauge repeatability and reproducibility study is conducted to determine the amount of observed variation that is the result of the measurement system. You use it to determine the level of GR&R variation is acceptable to industry norms. The Automotive Industry Action Group has established norms for a measurement system, and that's generally the criteria we use for that evaluation. Usually GR&R variation is calculated as a percent of tolerance. Some experts recommend calculating the measurement system uncertainty as follows. where we have the variance uncertainty equals the variance due to bias over time monitored on a control chart, plus our GR&R variance from a GR&R study, plus our variance for linearity. Linearity of a gauge is, you might have a micrometer and you might measure diameters from 1 inch to 3 inches. And we want to see that if there is any bias all the way through that range of operation, and if it's constant. And that's what that linearity test tells us. And then if temperature affects your measurements, you may want to include that variation. Fixturing can also influence the variation in your measurement, and anything else you can think of. So these are done with variances, not standard deviations. Generally, we like to talk in terms of standard deviation because it's in the same units as the mean. And if you remember that the variance is simply the standard deviation squared. So if I was measuring something in inches and I was writing out variances, they would be in inches squared, which is hard to relate to. So we take the square root of the variance and we're back to inches, and that makes sense to us. But mathematically, you can't add standard deviations. You cannot sum them mathematically. So we use variances. We calculate the overall variance, and then we divide it by the square root to get the standard deviation uncertainty and create a distribution for that. Okay, how does GR&R variation affect product inspection? When the GR&R distribution comes into contact with the specification limits, then there is a risk of making the wrong decision during inspection. Assuming that the gauge is perfectly calibrated so there is no error due to accuracy. So I'm basically gone back to this equation and ruled everything else out, okay? And we're just talking about GR&R. But in reality, if you have other sources of variation, you want to add them to come up with this variation uncertainty for your measurement system. And you could substitute that in for the distribution for just GR&R. But just to keep this simple, this conversation, let's just talk about GR&R's contribution to measurement error. A type 1 error is rejecting good product in error. And you can see here that I have the lower spec limit and the upper spec limit for my process. And the true value, the true measurement is X, the center of these distributions over here on the low side and high side. And because I have variation uncertainty due to my repeatability, if you think about it, GR&R really addresses precision in your measurement. That's the spread of repeated measurements. And so just due to this one source, I get a distribution. And what we do is we calculate the standard deviation associated with the GR&R study, and then we multiply that times 6 sigma, and we get this spread. And when this distribution comes into contact with your spec limits, and right here I'm discussing the lower spec limit, there is, even though this is the actual value, there is this probability that I would reject a good part. Okay. And then over here on the high side, when this distribution comes into contact with the upper spec limit, there is this probability that I reject this good part that measures well within my range. So I'm probably, if I don't have a really capable process and I'm keeping it centered, there are times where we're throwing away good parts. Okay. Now, worse than that is accepting bad parts, and that's a type 2 error. And the true value for the part is here beyond the lower spec limit. And there's this probability that I'm going to accept it. And you can see that when we are actually on the spec limit, there's a 50-50 shot of either accepting or rejecting. And the same is true over here for the upper spec limit. I'm beyond it, and there's this probability that I reject it. Now, when I worked at the 3M dental plant in Irvine, California, we won the state and the national Baldrige Awards. And so we had to be doing everything state of the art in order to do that. And so what we would do is take our manufacturing process, take that uncertainty, and we would move it within our spec limits by 2 sigma. And that would be our manufacturing spec. And then, so we had a tighter interval that we maintained. So we didn't get into this situation where we could be rejecting good product or more severely passing bad product. GR&R for attribute data. When a critical to quality characteristic is assessed, instead of being measured, we can use the attribute agreement analysis to determine the effectiveness of our measurement system. The attribute agreement analysis will tell us whether the appraisers are consistent with themselves, with one another, and with the known standard. Assessments can be either a binary rating, pass-fail, nominal rating, where we have categories with no hierarchy, or ordinal rating, where we have a hierarchy, such as 1 to 5, 5 being the best. And then we have SPC, Statistical Process Control. I think this is a tool that companies should be using a lot more than they do. And it's a very powerful tool. And I'm just going to go through it because I'm guessing most of you know what it is. But back in the old days, we used to do a lot of process capability studies. So we would set up control charts and with control limits, and then calculate CP/CPK, based on at least 100 data points. So I'm just going to go through this and quickly mention that the I and MR chart is often used these days for key performance indicator monitoring. And the I and MR chart can be used regardless of your data type, attribute, continuous, whatever, operations, manufacturing, transactional data. In fact, the top companies are using the I and MR chart for their KPI monitoring processes. A lot of benefits to that. Easy to make a mistake if you're not. Is continuous data better than attribute data? Continuous data is measured and has better resolution than discrete or counted attribute data. And by resolution, I mean more statistical power if you're performing statistical tests. Continuous data, all right, have more statistical power to perform statistical analysis with less data than attribute. With continuous data, where we have an actual measurements, it is easier to identify / understand sources of variation and draw conclusions. For example, with attribute data, a driver that is traveling in a 60-mile-an-hour speed zone is speeding and gets a ticket, either gets a ticket versus no ticket. But with continuous data, where we record the actual speed 68 miles an hour or 96 miles an hour, we have additional insight. At 68 miles an hour, we may conclude the driver isn't paying attention. Versus 96 miles an hour, we may conclude the driver is reckless. Okay, let's dive in a little further. To further demonstrate, consider the following example. Deliveries done as not on time and on time would be attribute data, and we can estimate the proportion late and on time. But if I used +1 for 1 day late and +2 for 2 days late, etc., and then used -1 for a day early and -2 for 2 days early, then we have continuous data. With continuous data, we can identify the process distribution for better understanding and analysis. We can determine process capability, confidence intervals for the mean and standard deviation, and how much to adjust the process when it's off target. Consider the 3 continuous data distributions below, with 12% non-conforming that are all different from each other and would appear simply as 12% non-conforming on a traditional P-chart. Thus, a continuous distribution explains the process center and spread of the process data. So, if you were just doing charting and proportion defective, what you don't know is where the center of your process is, and are you close to the upper spec limit or lower spec limit. In this situation, we're centered, and we've got 6% VAD in each tail, which means we're not capable. Over here, we have all 12% beyond the lower tail, lower spec, and the upper spec limit, could have 12% beyond there. And with just saying that you have 12% defective, you're missing out on all this additional information if you're not treating this as continuous data. And then we have some common attribute tests that I just want to go through here quickly. And want to spend a little more time here. Why do statisticians recommend n greater than or equal to 30? In my DOE training, I have a catapult and we set it up and launch a ball. And we set the arm length and the angle of release and the spring tension, etc., and launch the ball. And let's say I had it all locked in and we launched the ball 500 times. And I'm not going to get the exact same value. I'm showing here the data on what we call a frequency plot. And most of the time, I'm getting this data here at 75 inches, and most of the data is within plus minus an inch of the mean, okay? And then you can see we taper off, and there's a less likelihood of getting these smaller values on the lower tail and these higher values on the upper tail, okay? And when we plot the data on a frequency plot, and the height here all has to do with the number of times I get this value. So the value of 75, I'm getting maybe, 20, 25 times. The value of 78, I'm getting probably a couple times. The value of 72, I'm getting a couple of times. The value of 73, I got maybe 5, 6 times. Okay, so the data has shape when you plot it on a frequency plot, and that shape will help us determine the distribution our data follow. And that's important so that we use the right metrics to analyze our data. So here is a normal distribution. I'm going to assume most of you already know what that is. So I'm not going to say anything here because I'm short on time. I'm just going to move on. But I want to get a little bit into sampling distribution theory. The normal population distribution of individual X's, these are the individual launches, right, of our catapult. And we plot it in this plot, which is, we already said, was normally distributed. And so this is a distribution of individual measurements. And we have a standard deviation sigma. Okay, and then you can calculate a z value, and z equals x, some measurement, minus mu, the mean, and divided by sigma x. So z is essentially the number of standard deviations away from mu that any value x is. Okay. And then if we took this distribution, the statisticians are always busy guys, and they decided to sample, say this is a really large, our manufacturing process of infinite parts. And I'm taking samples from here of size 4. And I take, let's say, 500 samples of size 4, and I plot them in another distribution. Now, this is a distribution of X bars and known as a sampling distribution. You can see that it's getting narrower, and it's getting narrower because sigma X bar for this distribution is sigma X from this distribution divided by the square root of n, where n is our sample size. So if our sample size is 4, then this distribution is going to be half as wide. Okay, if my sample size is 16, then this is going to have a width 1/4 the width of this distribution, the parent population. So we use this theory to help us develop statistical power for our t-test and z-test and chi-square test, all of our different tests, well, not chi-square, but for our t-test, tests of means. And that's where this is going to come into play. And so z value then becomes z equals x bar, our sample mean, any particular sample mean, minus mu, divided by sigma x bar, which can be expanded x bar minus mu divided by sigma x divided by the square root of n. Thus, samples of size n taken from a normal population with mean mu and standard deviation sigma will form a sampling distribution for the mean that is normal and has a mean double x bar here in the center, and that equals mu, and the standard deviation sigma divided by the square root of n, okay, dictates our spread. And this particular proportion here is also called the standard error of the mean. So then the statisticians went a step further, and they came up with the central limit theorem, which states, regardless of the distribution of the parent population, the distribution of the means of a random sample will approach a normal distribution with mean mu and standard deviation sigma divided by the square root of n as the sample size n goes to infinity. So what does that mean in plainer English? Okay, on this top row here, I have 4 columns. And in the first column, I have a normal distribution. In the second column, I have a uniform distribution. In the third column, I have a bimodal distribution. That means we have 2 peaks. And then in the fourth column, I have an exponential distribution where the tail runs on to the right a long ways. Okay, this is what we call a highly skewed distribution. These don't look normal. but the normal looks normal. So these are distributions of individual measurements. But these processes that create these, if we go into those processes and take out samples of size 2 and plot the means, okay, the X bars for sample size 2, the normal distribution gets a little narrower. The uniform distribution is changing shape. The bimodal distribution is changing shape. It's no longer bimodal, with just a sample size of 2. The exponential distribution is starting to change shape as well. So now on this particular row, we go back into this row 1 where we have individual X's and our processes. And if I went into each of these processes and I took a large number, say 100 to 500 samples of size 5, where n equals 5, and I plotted those sample averages, my distribution for the normal distribution is getting narrower and taller. My uniform distribution is now looking normal at n equals 5. My bimodal distribution is starting to look pretty normal. And my exponential distribution is starting to normalize. By the time we get to n equals 30, so we go back up here and take samples of size 30 now. And if we took 100 to 500 and plotted them, and plotted the X bars for sample sizes of 5, the normal distribution gets narrower and taller. The uniform distribution looks the same. The bimodal looks pretty much the same. And even the exponential distribution looks normal. So the central limit theorem provides the rationale to make inferences about population means regardless of the shape of the population, provided the sample size is large enough, i.e. n equals 30 or larger. So rule of thumb is that the sample size n larger than 30 or equal to will adequately normalize the data mean regardless of the parent population and regardless of how skewed it is. So that's why statisticians will tell you to draw sample sizes of 30. Another reason for that sample size is that you're getting a pretty good estimate from that sample as to the true sigma, the true population standard deviation. You're within, at that point, about 30% of the true value. So if you've been wondering why statisticians always say sample size is 30 and larger, that's why. Okay, because the t-test requires that the data come from a normal distribution. And if you have n greater than or equal to 30, we can assume that we do have a normal distribution. Okay, what can we learn from 30 data points? So I've got an example here, and I worked in the IOL industry, and that's what we have here, an intraocular lens. These are replacement lenses for people who get cataracts. And then these things here are called haptics, and they have a diameter that's in the vicinity of 0.006 of an inch. And they keep the lens centered in the capsular bag when they remove your original opaque lens, so that you can see again when you're older, like you could when you're in your 20s. So at any rate, we are looking for a new haptic material supplier. So I've got 30 data points. And what can we do with just 30 data points? So I'm going to go into Minitab. And can everyone still hear me okay? Are you guys there? Hello?
Yeah, now we can hear you.
All right, thank you. Okay, so let's get into Minitab. And I've already entered the data, so we can save time. And the first thing I want to do is what I always do, is basic stats, and do a graphical summary. And I'm going to bring this column in for analysis, and the default confidence level here is 95%. I'm okay with that. Click OK, and Minitab provides this output. And so Minitab gives us a histogram and then fits it with a line for the normal distribution. And I look at it and I say, geez, that looks pretty bell-shaped. And I look here at my box plot, and I like to look at that to see if I've got any outliers. And that's an indication that my process is stable, but it doesn't verify it. If I really want to say if my process is stable, I should probably plot this data on a control chart, an individual X and MR chart, and see if everything's within the upper and lower control limits. Okay, so, but to verify that this is a normal distribution, I come over here, Minitab does an Anderson-Darling normality test. And when the p-value is above a 0.05, then we don't have enough evidence to conclude the data don't follow a normal distribution. Minitab also gives us our sample mean, standard deviation, sample variance, skewness, and kurtosis are measures of the shape of this distribution. Our sample size n, our minimum value, our first quartile value, our median, our third quartile, our maximum value. And it gives us 95% confidence intervals for the mean, for the median, and for the standard deviation. Now, for the standard deviation, this is only valid if I have a p-value that's above a 0.05. Okay, otherwise this is not valid. And then if you need to know what it is, you'll have to go in and do another analysis in Minitab, which we will do in the next example. Okay, you may want to go in and do a hypothesis test, one sample t-test. And we want to check perform hypothesis test. I do have a hypothesized mean of 0.0060, 6 thousandths of an inch. Options. By default, Minitab is using a 95% confidence level. That's what I want to use. And the alternative hypothesis is that the mean does not equal the hypothesis mean. So the mean, the population mean of our sample does not equal our hypothesis mean, which I said is our target of 6 thousandths. So let's hit OK. And Minitab's output, n equals 30 gives me my mean, standard deviation, standard error of the mean, and a 95% confidence interval, which is the same as we had previously in our previous analysis. And here's our confidence interval here, and they should agree and do. And then our hypothesis test, we get a p-value that's above a 0.05. So we don't have enough evidence to accept the alternative hypothesis, and we have to conclude that the mean is probably truthful. So, and when it comes to hypothesis testing, we never prove the mean. There's only, Minitab does have one test where you do prove the mean, where you prove the null hypothesis. But we're not going to get into that. That's an advanced tool. And the only time I've ever seen anybody need that tool is if they were a class 3 medical device or pharma company and they needed to introduce a new constituent into their product or process, and the FDA required they prove equivalency. But I don't want to get off track too much. So when it comes to basic hypothesis testing, we try to prove the alternative hypothesis, and if we can't, we presume that the null hypothesis is true. Presume it, we didn't prove it. And so because this value is above a 0.05, we are going to presume that the mean is 6 thousandths. Let's see here. I already knew that. Basically, by looking at the confidence interval, it tells me the same thing. If that 6 thousandths falls within this range, okay, then I know that I'm going to get the same result as the hypothesis test. Okay, now what else can we do? Let's do a capability 6-pack and see what our CPK is. So stat, quality tools, capability 6-pack for a normal distribution. You can see that this is dependent, this analysis, on you knowing if your distribution is normal. If it's non-normal, you have to come down here. And you have to know what distribution your data follow. And we're going to give that example next. So we're going to use normal. We're going to bring over our data. And subgroup size is 1. And then our lower spec limit for this raw material is 0.0055. The upper spec limit is 0.0065. And let's see here. Okay, I just want to know 1 points beyond the center line. Okay. Estimate, let's see, for subgroup size equal to 1, I'm going to use the average moving range. Okay, I'm going to go with the defaults. Most of the time, you're going to go with the Minitab defaults. Let's see, look at options. And it says number of subgroups displayed. I'm going to pick all 30. And then it says target. My target is 0.0060. And then use tolerance of 6 sigma. We'll do that. And display capability stats, CPs and PP. Okay. So let's just click OK here. Okay, and so Minitab gives us a control chart of our individual values, and you can see that all of them are in control. So it's okay then to estimate what our process performance is. If we're not in control, that would say that any of our analysis is questionable, okay? Unless you had an outlier in your data and you had a justifiable reason to omit it. Then your analysis, again, would be questionable if that weren't the case. But because we're in statistical control, our analyses are valid. And Minitab gives us a CP of 1.4 using our within variation. And then we have an overall variation. And Minitab, the within variation, is calculated using the moving range chart, and the overall variation is calculated from your typical standard deviation formula. And most of the time, the overall is going to be bigger because it can include special cause variation, whereas the within doesn't. And we can see here that we get 1.4 for CP, CPK 1.38, using overall worst case. And when it comes to PP and PPK, it can be short-term and it can be long-term results. In fact, we just have 30 data points, so this is really short-term. But basically, it's considered PP and PPK when we use the overall standard deviation, which is the formula, as opposed to the control chart version. And then we got 1.37, 1.35, and then we're fairly centered with 1.39. That's what CPM is. So we're looking good here. I would say that previously we were rejecting 10% that we were getting from our current supplier. We're checking out a new supplier, and it looks good based on the sample size of 30. I prefer to have a sample size of 100, but this is all we could get. And so, you know, so far preliminarily, things look good. Looks good for the future. Okay. So let's move on to our next example. Okay, what can we learn from 30 data points? In example 2, we have data that are non-normal. And how do we know that? We got a PCB board, PC board here that we designed, and we're testing, and we have a lower spec that we'd like to get time to failure 26 or larger number of hours, 1,000 hours of life out of this before they're failing on average. And so we've got 30 data points on a new PC board. So let's analyze that data in Minitab and see what we can learn. All right, so I've got the data here in the Minitab worksheet. And again, I like to start by doing basic stats and a graphical summary because it gives me a lot of information up front. What just happened there? I clicked on help. All right, we've got confidence level of 95%. That's what I want to use. So let's click OK. That help. And let's take a look at this. Okay, so our graphical summary, I'm looking at this and I'm saying that doesn't look so normally distributed. I'm also getting a couple of outliers. If the p-value is below 0.05, I'm going to assume these outliers indicate that the data are not normally distributed. If I have a p-value that's 0.1 or bigger and I'm getting outliers, I'm going to assume they are actually outliers and that the data are normally distributed. But we got a p-value here in our Anderson-Darling test results that is below 0.05, implying that the data do not follow a normal distribution. And so out of all of these metrics, The one that's not valid is the 95% confidence interval for the standard deviation, because that's done using the chi-square test, which assumes the data are normally distributed. So let's find out what the true confidence interval for the standard deviation is. Stat basics of one sample variance. And let's bring over the data. We're not going to perform a hypothesis test. Our options. Yes, we're going to create a two-tail interval with 95% confidence level. So let's click OK and OK. And Minitab gives us this result. It says Bonet's method is valid for any continuous distribution, regardless of the distribution the data follow. And chi-square method is valid only for the normal distribution. So we're going to be using Bonet's. And so you can see that range is obviously wider than the chi-square distribution. So that's a price you pay when you're using non-parametric tests, but at least we do have a confidence interval. If somebody were to ask us, we'd have to give this result and not this result. All right, next, now that we know the data are not normal, and we'd like to do a capability analysis, let's identify what distribution our data follow. So quality tools, individual distribution identification. Okay, single column, I'm going to click in it, and then I can double left click and bring it over. Subgroup size is 1. And then I'm just going to go with the default settings here and click OK. And then Minitab is going to try to fit 12 different distributions, no, 14 different distributions to the data. And then it also does 2 data transformations. One of them is a box Cox, and that's this one. So okay, we failed the normal distribution, as we already know. Box Cox, we could transform the data if we wanted to do that. It doesn't fit a log normal. And a 3-parameter log normal would be acceptable. We do not get a p-value here. The only 3-parameter distribution Minitab gives you a p-value for is the Weibull distribution. Now you're left to just take a look at the diagram and the p-value, the A.D. Anderson-Darling value. Values below 0.5 would be acceptable. The lower, the better. Okay, so that's a possibility, the 3-parameter log normal. Exponential, no. 2-parameter exponential, yeah, that would work. A Weibull 2-parameter, no. 3-parameter Weibull at 0.5, that's really good. And you can see the data are well within the limits here. Next to the line, follow that line through the data very well. So that is our best candidate, and to save time, this is the best candidate. So we're going to use the Weibull, 3-parameter Weibull distribution. Okay, so let's go ahead now and do our capability analysis. 6-pack, non-normal. And our data, let's bring it over for analysis. Subgroup size 1. The Weibull is your default in Minitab, but we want the 3-parameter Weibull, so we have to select it. And then my spec, and I have a one-sided spec here. That is 0.26000. And I'm just going to click OK, go with the defaults. And we get our output. Okay, so it looks like we are in statistical control. And let me say a couple of things about this. This distribution is done not based on, this is an eye chart, but it's not done based on the normal distribution. It's done based on the Weibull 3-parameter distribution. Okay, so these limits are good. We're not going to get a lot of false alarms where we get out of control data points. If this were a normal distribution and I put a line here, it would be about here somewhere. And you would get some false alarms where this is the way this distribution behaves, but you would get it above the upper control limit and think you should investigate when you shouldn't, when you don't need to. So that's the beauty of this. We get an eye chart with the correct control limits based on the actual distribution of our data. And we are in statistical control. So when you want to use the eye chart for data that are highly skewed, for example, you would want to identify the distribution, use this capability 6-pack tool, and identify these limits and put it on the eye chart that you manufacture instead of using the spec limits that are based on the normal distribution. And then that will perform very well for you. Okay, and we've got a PPK of 0.64, which means we've got some work ahead of us. Our threshold is below what we wanted. We can either lower our expectations on this newly designed board a little bit and have a capable process, or we can stick to our guns and do some process improvement, or at this point, probably design improvement, which could be process improvement related as well. I don't know if you know that quite often the performance of a product is very dependent on the process being optimized as well as being designed properly. So let's minimize this. So we learned a lot from 30 data points. And if we're going to stick to our guns, we've got a little more work to do here. We can look and find out why we are getting these, not making our time for reliability. And if we're lucky, it's, one component mostly, and we can just upgrade it if we're lucky. Okay, so now I want to get back to the presentation, but you can learn a lot just from 30 data points. Now, obviously, those capability values are indicators. I wouldn't, celebrate Yahoo at that point. Those are indicators because the sample sizes are small. You'd like to have at least 100 data points if possible. And then see those kinds of numbers, particularly for the normal distribution. We'd like our process capability, no matter what the distribution, to be 1.33 or better. And that gives us some opportunity to have process drift and shifts a little bit and still not be producing very many rejects. Okay, so let's get back to this. And I'm close to the end here. Don't we need normal data in order to use the X bar and R chart and the I and MR chart? The answer is no for the vast majority of the time. The X bar and R chart benefits from the central limit theorem. If the distribution is skewed, then using a subgroup size of 5 to 8 samples will generally be sufficient. Now, if you want to calculate CP and CPK and PP and PPK, as we just discussed, This works for the control chart to work to tell you if your process is being influenced by special causes. But if you want to calculate capabilities, CP, CPK, then you need to understand what your distribution is and do what we just did. Okay, for the I and MR chart, also a great tool to use for KPI monitoring. Doesn't benefit from the central limit theorem, but the brute force of the 3 sigma control limits is generally sufficient for the vast majority of data distributions. Remember, the objective is to separate out the special cause variation from the common cause variation. Thus, we just need control limits that almost cover all of the common cause variation as demonstrated in the graphs below. So, here's our normal distribution, and our 3 sigma limits should include 99.73% of our data. And over here, where we have this, skewed 3-parameter Weibull, which is not a normal distribution, it's truncated on one side, and then it runs long on the other side. But even with this distribution, based on plus minus 3 sigma limits, I've drawn them in here. Okay, and it's centered on our mean. 99.8, actually more of the data fall under that spec limit, under that control limit. And thus, we're not going to get a lot of false alarms with this process. So I could put this on a regular I and MR chart, even without the improved limits based on the distribution type, and I'm not going to get many false alarms. So just on the brute force alone of 3 sigma limits, you can use the I and MR chart. A lot of people will tell you the data need to be normally distributed. That's only true for a small percent of the data distributions. Okay, last slide. I do have some quality training courses if you're interested. Courses contain theory, longhand, and some Minitab solutions. I've got the Certified Quality Engineer training course. And if you use this discount code, you can get 30% off. The same is true for the Certified Six Sigma Black Belt. These are good prep courses for the ASQ exam. And then I also have what I call Quality Engineering and Six Sigma Black Belt Statistics with Minitab. So you'll learn Minitab as well as your high-end, statistics. It's these other courses, you're just going to learn longhand. All right, because we're just prepping you for the exam. But this particular training here, Quality Engineering and Six Sigma Black Belt Statistics with Minitab, is geared to help you be a good professional quality person. And I have other formats available for classroom training and half days, full days. And I also do design of experiments training, and that's available via classroom training as well. So if you're interested in any additional training, please contact me. And that ends my presentation, and I'm ready for any questions anybody might have.
Thank you very much, Ed, and that was really interesting. I have to admit, and I'm sure Lucinda will agree with me that the math is sometimes a little beyond me there. But we do have a couple questions that came in, and the first one is here on how relative is the normal distribution as it relates to hypothesis testing?
Well, if it's hypothesis testing, I hope I already answered that question because I did a normal distribution and a non-normal. When it comes to the assumption that the data follow a normal distribution, we're fairly robust when we're doing hypothesis testing of the means or a confidence interval of the means. But if we're doing hypothesis testing regarding sigma, the standard deviation, then the data do need to follow a normal distribution, or you'll have to use the non-parametric result. And there's other more advanced ways to come up with a tighter interval using reliability techniques. I hope I answered your question.
Hey Ned, this is Sam. Yeah, you answered the question, and that helped out a lot because I remember having an instructor when they taught the black belt course through ASQ at the organization that I work at, and the instructor at the time was talking about, this was probably 5 years ago, that they were looking at just completely throwing the distribution type, and for lack of a better term, just getting rid of it when you're talking about testing means. But that is a good point that you brought up about standard deviation, because that was something that I was not or I haven't been aware of recently.
Okay.
And sorry, Ned, we did have another question that was in the chat, and I think it was answered, but I'm going to read it anyway.
Okay.
As in MSA Minitab sets three thresholds. Excuse me. If R&R percentages are greater than 30%, then the measurement system is not adequate.
Correct.
30%, then it's marginal. What does marginal mean? And someone has gone ahead and answered that marginal in MSA equals low confidence.
Yeah, it's okay. It's okay. So, okay, marginal means the measurement system being appropriate depends. It depends on, how certain you need it to be. And again, I went through that GR&R slide. Let's see. Give me just a second here. The bottom line on GR&R is really this slide right here. Do you want to make the right decision when it comes to inspection? And the more uncertainty you have, the more GR&R, variation, uncertainty from that variation, the higher the probability that you're making type 1 errors, which aren't in jeopardy for your customer, but type 2 errors are. And you don't want to be, if you're a medical device, you don't want to be passing along a bad product. I hope I answered the question appropriately.
Yes, I had a kind of a idea, but yeah, you clarify more the concept for me. Thank you.
Okay.
And did anybody have any further questions for Ned?
You guys can, I'd like to just make a statement. Whatever questions you have, if you got something more detailed, you think this is a hard format to discuss something, you got a statistical challenge or a question at work related or presentation related, whatever, send me an email and I will respond. Okay, and my phone number is right here, this 949-525-1687.
Ed, this is more of a curiosity question. So on the example that you had where you're measuring the diameter and your data was 6 places to the right of 0.
Yes.
What you used to measure that with, and what was your R&R on that measurement device?
Okay, I just made up that data because I used to be in the industry and I'm familiar with that. We had a very, very precise optical reading device that would measure that diameter out to, 6 places. So I just made up that data for analysis purposes. So I don't know what, I don't recall what, the GR&R would have been on that particular instrument, but we had it down to, probably 1/10 of a tenth, the measuring resolution of our gauge.
Thank you.
Anybody else?
But let me give you my, okay, let me see if what I don't have here is my email address. I gave you my phone number. Let me give you my, do you have my? I don't have it written anywhere. I can
Yeah,
give it
Ned,
to
this is
you.
Ben. If you send me your slides afterwards,
Yes, I'll do that.
I
Can
will
you
put
send
them
me an email? Is this Dan? Is that who you said?
Ben.
Ben. Okay,
Yeah.
Ben. Okay, Ben, thanks. If you can send me an email and then, yeah, you can give out my email address. You
Sounds
can
good.
forward that information so that they can contact me with any questions.
Will do.
All right, no problem.
And thank you so much, Ned. This has been great.
Okay, great. Well, it's nice getting to know everybody. And have a great weekend that's coming. I'm headed out of town. We're headed to visit some family. But I'm bringing my laptop, so I will respond to any questions.
All right. Well, thank you everyone for attending tonight and looking forward to any ideas that you do have and send to myself or Ben or just the general ASQ mailbox, and we'll try and pick those up. And again, if you have any desire to volunteer or do anything with the 1404 group, we are more than happy to utilize your skills. And we will reach out to you as soon as we can. Just let me know. This is Ann, and you'll receive stuff from both Ben and I on your continuing education units in the next probably week or so. And hopefully next month you can join us for our next presentation and have a great time in between then and a nice Labor Day holiday. Thank you, everyone.
Thank you.